Hello everyone, I hope you guys are doing well. So in today's video, we are going to be walking through the 2025 VCE or VCA Physics exam part 2 of the short answer questions. We will be basically going through question 11 to I think question 19 of this paper. So yeah, I hope this walkthrough helps you with your physics study. And if you find it useful, please make sure to like and subscribe and share it with your friends or teachers because it really helps out support this channel. And like always, guys, if you are always interested in private tutoring in methods, physics, chemistry, or specialists, you can always reach through my email. And now let's smash through this video. All right, let's go. Okay, question 11. Janine is a poultry farmer. She is interested in using renewable energy to supply the power in a shed containing heat lamps for a chicken incubator. She uses a wind turbine that supplies an AC voltage of 230 volts RMS and can deliver up to 5 kilowatts of electrical power. The best location for the wind turbine is 900 meters away from the shed. The total resistance of the wires connecting to the turbine and the shed is 6 ohms. The system is represented schematically here. Beautiful, not too bad. Each lamp is designed to dissipate 70 watts of power and is intended to be operated with a minimal voltage of 210 volts RMS. Show that the current through the lamp under these conditions is 0.3 amps. Beautiful. So we know for a fact we have the we have the power and we have the volts. So we know that P is equal to voltage times current. And so we're trying to calculate current. So current has to be, of course, power over voltage, which in this case is 70 over 210, which gives us, so what's 70 divided by 210? That gives me 0.33. Beautiful. So same thing as what they've got. So we've shown that. Nice. Next question. Janine connects a number of heat lamps in parallel in the shed. So in this shed, she connects the heat lamps in parallel. This is a very important word. We're going to explain why. You remember there's two types of circuits, there's series and parallel. When the wind turbine is operating, the potential difference across the shed is actually 210 volts RMS. How many heat lamps have been installed? Show you working out. It's 3 marks. Okay, so let's actually think what's happening here. All right. So what I'm going to do is I'm going to just represent this diagram in a nice, what do you call it? In a circuit diagram. So we have of course, the wind turbine, which produces 230 volts. And that's producing AC, and it's all going to, of course, let's draw a resistor. This resistor basically represents the the transmission wire resistance, which is, of course, this wire is 6 ohms, and it is beautiful 6 ohms. And then the shed here, which I'm just going to draw as a little box here. I'm going to call it S, which means the shed, yeah, like that. Beautiful. Okay, so this is what it looks like, and we know that they said that the potential difference, so the voltage across the shed, they found out that it was a 210 volts, yeah? This is very important. So that means, guess what? If we were providing 230 volts and only that what reaches the edge is 210 volts, where the hell did that 20 volts go? Of course, it went to the transmission line. It was lost in the transmission line, yeah? Easy? Just remember that. It was lost in the transmission line. So, okay, we know that. And in the shed, yeah, they told us that the lamps are in parallel. What does parallel mean? It means, remember, when you get a circuit in parallel, like this. We kind of draw an example. So imagine these are the lamps right here. And if they're all in parallel, like this. So if they're all designated in parallel, like that, parallel, whatever. The thing about parallel circuits is these are all crosses. These are the thing. Yep. The thing about parallel circuits is that the voltage stays constant. So you know how we have 210 volts? All of them get the same voltage. You know this gets 210 volts. This gets 210 volts. This gets 210 volts. What happens is the voltage stays constant. But what changes and what splits up is the current. So imagine that we were providing here 3 amps, yeah? 1 amp will go here. You see, sorry. 1 amp will go here. So remember 1 amp will go here. So the current is what splits up in a 1 amp here. And yeah, do you see how the current splits up? That's very important. So current splits up, whereas the voltage stays constant. Because this is very important to do this. And okay, so why is this important though? We can actually, well, we know for a fact that, we know that you remember how we said the current splits up, yeah? This here, the one that we've calculated here, this is the current for 1 lamp, only 1 lamp, yeah? And our goal is to find how many lamps are there installed. So what current reaches the shed? That's important. Well, we actually, it's kind of easy. It's in a series circuit. Do you see how it's a series circuit? That means we just need to find, for example, we just need to find the current, and the current runs through all of the whole circuit the same. For example, let's calculate, the most easiest is using this, because we can actually easily calculate the current through what's passing through here, because we've got the voltage and the resistance, which of course we use Ohm's law, which is voltage equals IR, hence it's 20 over 6. Your current is 20 over 6, which gives you 3.33 amps of current that passes through this, yeah? So imagine 3.33 passing through all of this. That means it's passing through the shed. What passes through the shed is that 3.33 amps, yeah? For that example that we gave, yeah? I'm just going to kind of go backwards to, I don't know why I deleted that thing. I'm just going to cut that and go backwards to the thing that I was drawing. Okay, let's go back to this. That means, you know, this current that we're producing, this working out here, that means where we're giving, that's coming to the shed is 3.33 amps. You remember what we said? It splits up, but we don't know how many lamps there are. But luckily, it splits up fairly, yeah? We know 100% that each of these lamps consume how much? We know that they consume each 0.33 amps, yeah? So imagine this one here consumes 0.33 amps. This one also 0.33 amps. And yeah, so you know what we can actually do to calculate how many lamps there are, yeah? Shouldn't we, this 3.33, yeah? The total current, shouldn't we divide it by how many each lamp there is, how much each lamp consumes? And then we can absolutely calculate how many there are. So doing that, it gives me 10, basically. There should be 10 lamps that are inside there. Easy. Very, very nice question here for 3 marks. Next question, C. Jasmine's friend Zana suggests including a transformers T1 and T2 as shown in the figure 16 to increase the number of heat lamps that can be powered by this wind turbine. A very typical question. This always comes up. I love these ones. Beautiful. So they put 2 transformers. Identify the specific types of transformers, step up or step down, that should be used for T1 and T2. Of course, guys. This is very easy. Of course, T1 is a step up, and I'll explain why. So, of course, T1 always is a step up, and of course, T2 has to be a step down. And this is all dependent, of course, on power loss on those transmission lines. Think about it. What happens is this. We know that power is ideal. The transformers are ideal means power is not lost. So you know the power here. Imagine this power here that this gives is, I don't know, let's say 30 watts. I'm making it up, but yeah. So because the transformer doesn't lose any power, what comes up here is 30 watts of power to the transmission lines. And guess what? What's beautiful about this is, can you see how power is constant? This is very important. So if we step up transformer, yeah, the thing about the problem with these transmission wires is that because they have a lot of power loss, if you don't know, from this formula, P equals I squared over R. And that's due to the fact that the current is high on these wires. And what our goal is to decrease that current, because if we decrease the current, the power loss on those wires is actually small, which is the goal that we're trying to do, yeah? So how do we do that? Well, the best way is doing increasing the voltage in these transmission wires. That's why we use a step-up transformer here. For example, if the voltage is 230 and let's say we stepped it up to 1,000, yeah? Why is this important? Because, look, if we use P equals VI, remember how power is constant? What happens to the current? So imagine P is constant, yeah? But if we increase the voltage, what happens to the power? What happens to the current in the wires? It decreases. And that's the goal. So we will have low current in here. And remember, what does low current have? Using this formula for power loss, low current means less power loss in those transmission lines, hence more power will be received through the shed, which is actually better. Does that make sense? And of course, what does a step down transformer actually do? It basically, you know how it's a high voltage that is received here? It steps it down to the normal, it steps it back to the normal voltage, so this one would run optimally, basically, or in a suitable level for the lamps to work. Make sense? So it's a very typical question, very typical scenario. I love these type of questions because they're very easy and they always come up in exams. What's the next one? Justify your choice for step. Okay, this makes sense. Yeah, like okay. Well, let's just talk. Well, we basically said everything here. So what we could say is using a step up transformer. I'm gonna write a lot just for you guys to read and understand. So I'm saying using step up transformer increases the voltage, in this case, transmission voltage. Be careful. We need to actually be more, because, you know, which voltage are we talking about? The transmission lines. Transmission voltage, which reduces the current. For the same power. Because remember, it's ideal. Same power. Which from this formula, P equals VI. Make sure you put formulas to show the examiner as it's ideal. Beautiful. Hence, a smaller current, reduces power loss. Loss in the wires. From this formula, P equals I squared over R. So less power is wasted. In transmission lines. And more power reaches the shed. And then the step down transformer. Of course, you want to write it much more shorter, like in dot points, but I'm trying to be as very, so when students can read this, they can understand what's happening. Where the step down transformer brings down the voltage to a suitable level, for the lamps. Basically allowing more lamps to work, to be powered better, All right, that's perfect. So yeah, I think that's a better response. It's a very detailed, of course, just for students to understand. But yeah, that's how you do these type of questions. I love these type of questions because they come up every time in exams, and it's so fun to do them because yeah, that's why. Do as many papers as you can. Very beautiful question. Let's get into question 12. Denzel is using a demonstration hand crank generator. A schematic diagram of a generator is shown in figure 17. The generator contains a rectangular coil with side lengths of 5 centimeters and 2.5 centimeters consisting of 20 turns of insulated copper wire. The coil is rotated between two bar magnets that provides a field strength of 0.6 Teslas between the magnets. Denzel rotates the coil at a frequency of 50 hertz. Beautiful, just typical question, looks like. State why the flux through the coil changes as the coil rotates. How the hell do you explain that? That's quite obvious. State why the flux, through the coil changes as the coil rotates. What? That we know for a fact, guys. We know when the coil or the rectangular coil is horizontal in direction. Do you see how the field lines? So think of it like this. If it's like in this direction, and can you see the field lines are not passing through the field lines are not passing through the area of the coil? That means that, because remember flux, the formula is area times your magnetic field, basically. So do you see how they're not passing? So your flux is 0. And so when it rotates 90 degrees, so in the vertical position like this, then in that case like this basically, then all the field lines pass through it, hence it is at its maximum flux. And imagine you're rotating, you just keep rotating, it's in this direction, then you rotate, so you always have this basically change in flux occurring. So basically you could say that angle between, like, that kind of, it's so, I've never seen a question because it's so easy, but you don't write it. That's kind of a but yeah, basically just the angle between the magnetic field, so these field lines, and the coil area just changes as you rotate it. That's probably what you just want to say. It's only 1 mark, so we could say, this is so bad. Like, I don't like this question because it's like so simple that you don't know what to write. So coil rotates, the angle between the magnetic field, and the coil's area changes. So the magnetic flux changes. So the magnetic flux changes. changes through the coil. So changes through the coil. That is so like confusing. That's like the way to write it is just so confusing. Yeah. As the coil rotates, the angle between the magnetic field and the coil area changes to the magnetic fluctuation. Like, it's just confusing. Like, yeah, it's so easy, but like, yeah, you can never to explain it. It's quite crazy. B, yes, love calculation. Show that the change in flux of as the coil rotates from the horizontal. Remember the horizontal, that there's no field lines, so the flux is 0, and to a vertical position where the flux is to the maximum. So basically, yeah, is that so easy? So the change of flux is basically just try to calculate the maximum flux when the follows. Yeah, so we know that flux, we remember it's the basic area times your magnetic field. So in this case, our area is, so it's 5 centimeters to 2.5, so make sure it's a meter. So 5 times 10 to the negative, so centimeters is -2 to convert it to meters, times 2.5. Yeah, 2.5 times 10 to the -2. So that is going to give me my area, and times it by the magnetic field, which is 0.6, it says. And that is it. So that gives me 5 times 10 to the -2 times 2.5 times 10 to the -2. 0.6. And that gives you the same answer as what they've given us here. 7.5 times 10 to the power of -4 Webers. Done. Beautiful. Very, very easy question for a mark. Question 3. 3 marks, calculate the average EMF induced as the coil rotates through the quarter of a turn from the horizontal to a vertical position. Beautiful. Very, very typical 3-mark question. Love it. So yeah, basically we're trying to calculate the EMF, and we know that EMF is -N, change in flux over change in time. All right. So first of all, what is our N value? Okay, what's how many like coils do we have? 20 turns. We have 20 turns. We already calculated change of flux for when they're going from a horizontal to a vertical position. It's that 7.5. So 7.5 times 10 to the power of -4 Webers. Yeah, stop checking. Yep. And the change in time. Well, to calculate change in time is okay. So we're given the frequency. So first, let's calculate the period. We know that period is 1 over the frequency. Yeah, which is 1 over 50 in this case. Is that correct? Yeah, 1 over 50. Yeah. That gives me 1 over 50. That gives me 0.02 seconds. Remember, period is like a whole revolution, a 360 degree. Because we're doing a quarter of a turn, we divide it by 4. We're not doing a whole 360. We're only doing 90 degrees. So divided by 4, and that gives me basically my change in time at 0.005 seconds. And put that in there. Done. That gives me times 7.5 times 10 to the -4 over that, and that gives me 3 volts. That is so how many significant figures though? 2. So 3.0 volts. So 3 volts. Very nice. Beautiful question. Very, very typical. So make sure you do a lot of past papers like these. These are very typical. D, say a change to the setup in figure 17 that could produce a DC output from the generator. Give you a reason. What a beautiful question. This is the most common type of question. Of course, we are using currently slip rings, which gives us an AC output. So to change it to DC output, what we need is a split ring commutator. Replace those split rings with a split ring commutator, and then because it's 2 marks, I will give you 1 mark. Then just define what a split ring commutator. So remember, putting a split ring commutator basically just reverses the connection every half turn. Hence, the output current is DC. And yeah, so just for the guys, yep. So remember, when it's a split ring commutator, right? Split ring commutators, it's AC, and what when you replace them with a split ring commutator, all of those start to get rectified. All those negative values get rectified, and so it becomes DC. For those that don't know, and so that's what we just need to write. Very, very easy. 2 marks. I'm not gonna lie. So nice. So what we're gonna say is 1 mark. Just basically we say replace the slip rings. The very common question, by the way, slip rings. With split ring. So wait, split ring commutator, and then as a split ring commutator reverses just the definition that you would have in your summary or in your notes. The connection, reverse the connection, so every half turn. So the output current flows in one direction, flows in one direction, producing a DC output. Easy. Beautiful. So this is a very common, so make sure yeah, do a lot of past papers for this. So next question is question 13. Diffraction patterns can be produced by directing electrons at a graphite foil. Electrons are emitted by a hot filament at the cathode, accelerated by the anode, and hit the target graphite foil, producing a diffraction pattern on the fluorescent screen. Beautiful. This is a very common type of experiment. A diffraction pattern is observed using electrons of a de Broglie wavelength of this. So we actually have the wavelength of the electrons, which is great. Determine the accelerating voltage applied to the anode that is needed to produce those electrons with this wavelength. Easy. Okay. So we're actually given the wavelength of these electrons. So let's write that down. So we're given the wavelength, which is 1.2 times 10 to the power of negative 11. Now, this is actually very useful. What we're trying to calculate is the voltage. And the only formula that comes just by looking at my summary sheet is that we know that kinetic energy is equal to QV, where this has voltage in it, and that's the goal. Now, we know also, by the way, that kinetic energy is also equal to P squared over 2M. Yeah, why is this very useful? Because we have the wavelength, we know that the momentum, we can calculate the momentum by h over wavelength. Look how beautiful that is. So we have the wavelength, we can easily calculate the momentum. Put momentum in this formula, we will calculate the kinetic energy, and when we get the kinetic energy, we can divide it by Q and get voltage. It's a very beautiful formula. Now I'm just going to put these together. These two I can just put together because they're both equal to kinetic energy. So it's just QV is equal to P squared over 2M. Easy, so like that. And like basically rearrange this, get rid of this Q because we want to get voltage, so Q would be here. Because multiply both sides by 1 over Q and we'll get that. That is the best formula. Now, this is what we're going to use to calculate the voltage. Now, let's just calculate the momentum. Momentum is H, which is, in this case, 6.6. What is it, actually? Just double checking on my summary sheet. Let me just put it there. Okay, so what is Planck's constant? Is 6.63 times 10 to the negative 34. All right, and over the wavelength, which is 1.20 times 10 to the negative 11. Done. So let's do that. 6.63 times 10 to the negative 34. 1.2 times 10 to the negative 11. And then that gives us, just double checking if I've done everything. So it gives us a momentum of 5.525 times 10 to the power of negative 23. Now we've got the momentum, we can actually sub everything in here. So we know the voltage is going to be just equal to, putting a very big thing. So it's going to be our momentum, which is at 5.525 times 10 to the power of negative 23 over 2 times the mass of the electron, which, just looking at my thing, it's 9.11 times 10 to the negative 31. And the, what do you call it, the charge of an electron, which is 1.6 times 10 to the negative 19. So hopefully this gives us the voltage. Oh, don't forget to square that. I fully forgot to square that. Square that. 2 times 9.1 times 10 to the negative 31. 1.6 times 10 to the negative 19. That gives me basically 10.482 volts. Now, of course, we want it in kilovolts, so divided by 1,000. And that gives me basically, to round it up to how many decimal, to 3 significant figures, that's basically 10.5. 10.5 kilovolts that we're going to need. Beautiful question. Very nice for 3 marks. All right, so question 14. Explain how the null result of the Michelson-Morley experiment supports Einstein's special relativity. Okay, beautiful question. This question has been coming up quite lately. It's because it's in the new study design, and it's a copy of a paste of the same question from the sample paper. So like I've always said, guys, make sure you have a response for this in your summary sheet, because it's always one of the most common types of question, especially in this new study design. All right, let's get into it. So basically, the Michelson-Morley experiment was, the purpose of it was just to detect if there was this ether, which is like a hypothesized medium that light used to travel, yeah? And so the purpose was just to detect a difference in the speed of light, yeah? Because you know how the Earth basically moves through the ether? There should be a difference in that speed of light. And if there was, like if the ether did actually exist, for example, light that's traveling through the motion of the Earth will have a different type of speed, that is when it's traveling perpendicular to it. Hence, giving us like an interference pattern. That's the thing. But you know, when they did the actual result, that they found like a null result, means it didn't work. There was no change in that interference pattern. even though they changed like the equipment and the apparatus, they did it in different days, different seasons, and it was just always the same. There was no change in that speed of light. And so basically this kind of gave us the idea that the speed of light is the same for all directions, and it's actually independent in the motion of the earth. It doesn't depend on the motion of the earth. And then of course this supports, you know, Einstein's second postulate, which of course states that, you know, the speed of light is constant for all observers and does not depend on the source or the observer. I remember the Einstein's special relativity second postulate. So yeah, do you see how it supports the Einstein special relativity? Because this result, yeah, it basically did kind of stop, you know, there was nothing, the ether did not exist 100%, and yeah, there was no change in the speed of light. That was the point of the experiment, yeah? So I'm going to write a response. Please make sure, if you don't have a response, write my response. I'm going to try to make it as detailed. I'm going to try to write a lot just to get the most detail into it. What I basically explained, and yeah, let's smash through this. So what I'm going to say is explain how the knowledge of the Michelson model. Okay, so we're going to say the Michelson morally experiment aimed to detect differences in the speed of light due to Earth's motion through the hypothesized. Remember, they were hypothesizing that there was an ether, this hypothetical medium. Hypothesized ether. I know my spelling's wrong, but who cares? At the end of the day, just get the point in there. So if the ether existed, light traveling parallel to the Earth's motion would have a different speed to light traveling perpendicular to the Earth's motion, traveling perpendicular to it, resulting in a shift in the interference pattern. So they had an interference pattern to see the shift. Okay, beautiful. So I think this kind of gets it doesn't get all of it, so we're gonna, because then we need to talk about, however, the experiment produced, of course, a null result, so it didn't work. Produced a null, so no change, null result, showing no change in the interference pattern, in the interference pattern, regardless of the orientation, we said, of the apparatus. So they moved the apparatus. So this indicated that the speed of light is the same in all directions. And independent, we said, independent on the Earth's motion, Okay, we've got that. Now, what we're going to write also is this result. So now we're going to explain how it supports Einstein's second postulate. So this result supports Einstein's second postulate, which states, of course, which states that the speed of light in a vacuum is constant for all observers, and does not depend depend on the motion of the source and observer. So look at that. Overall, this is very detailed one, and you want to write something like this. Now, don't write it in an exam, but this basically, I would suggest putting in your summary sheet. What I've written here is one of the most common types of question that comes up, and you can always just look at this and know what to write and dot points. So look how beautiful it is. It kind of, basically, the whole question is answered because we've actually explained the Michelson-Morley experiment. What was the meaning of it. We explained how there was a null result and hence how it supports Einstein's special relativity second postulate. Look how beautiful. And this is, I've done the same question, I'm not gonna lie. So I've already have this type of scenario already in my summary sheet. So whenever I get this question, I look at my summary sheet, write it like that. So I've kind of memorized how to write this, and you too can do that, especially in your summary sheet. Make sure you write something like this, or you can use my example, of course. And yeah, this will really help you in an exam because this question is now coming up quite a lot. It's in the new study design. Perfect. So let's go down to question 15. In a young double slit experiment, a green light source of wavelength 550 nanometers is incident on two slits. The resulting interference pattern on a screen situated 2 meters behind the slits included a group of bright bands that are 2.75 millimeters apart. This setup is shown. Beautiful. Calculate the split separation. Easy. We know that change in x is equal to wavelength L over D. And we're basically calculating D, which is the slit separation. We know our change in x is 2.75 times 10 to the negative 3 to convert it into meters. Our wavelength, they just gave it to us. Our wavelength is 550 nanometers, and times the length, which is 2, and this is your distance. So that will be, using calculation, so it'll be 550 times 10 to the negative 1 times 2, all over 2.75 times 10 to the negative 3. That gives me basically 4 point, how many was this? Looks like 3, 4.00 times 10 to the power of, so 1, 2, 3, 4, to the power of negative 4 meters. That is your slit separation. Very nice, very nice. Next question, the green light source is replaced with a light source of a lower frequency. Explain the effect of changing the light source will have on the interference pattern observed on the screen. What a beautiful question. Every year they have this question. So it's a very common type of question. So what we need to do is, okay, think about it. What does low frequency mean? If you have a low frequency, yeah, it means you have a high wavelength. Yep. And of course, if you have a high wavelength, looking back in this formula, if you have a higher wavelength, which is this part over here, wouldn't you have a higher change in x, which means the pattern or the interference patterns is more spread apart. And that is it. That's how you would explain it. A very type of easy question. So what we're just going to say is, so low frequency means higher wavelength. Yep, so it means highway using change in x equals wavelength L over D. High wavelength increases change in x, so the slit separation, hence the pattern is more spread. Hence the pattern is more spread. Beautiful. Next question, question 16. Jessica and Matthew investigate a photoelectrical effect. They expose a metal sample to a light of constant intensity but varying frequency and measure the voltage required to stop the most energetic electrons. This allows them to calculate the maximum kinetic energy of the electrons. The data collected is plotted and a trend line is drawn beautifully. Okay, using figure 20, calculate Planck's constant. Easy. So we know Planck's constant basically is just the gradient of this line. And so we're just going to need to take 2 points that are nice. Like, for example, this point is a real... Let me use red so you can see. For example, I can see this point's a really nice point on the line, and you know this point. Let's say this point. This point here. And this point is on the line of that fit. Alright, so it should be right over there. Okay, so we're using the gradient. Remember, to find the gradient, it's y2 minus y1. So your Planck's constant is just the y values first. So, for example, so this is 4 easily. This one here is, I think it goes by, so what are the, so I think it goes by, okay, so for a 12, so this will be 9.2 if I'm not mistaken, yeah? Was 0 0.4, 0 0.8, 1.2, 1.6, and 10. Yeah, that's perfect. 9.2, so it'll be basically the y value, so 9.2 minus that 4, all over the x values. So which is 26, so this value over here, minus 14 times 10 to the power of 14. Don't forget this over here. That gives you 9.2 minus 4, 26 minus 14, 10 to the power 14. That gives me basically, looks quite nice. So it gives me how many decimal? Let's say 4.3. Just let's say 4.3 times 10 to the power of a negative 15. Is the answer for that one. Beautiful. I'm not gonna actually highlight it so you can see the answer. Done. Next question. Using figure 20, determine the work function for this metal used. Easy. So we know that the work function is basically the y value, the y-intercept of the graph. So if I took this graph over here and I just consistently kept going, following it, yeah, like this. Do you see how it's just crossing -2? That's the y-intercept. So it's 2, basically. 2 electrovolts is our work function. You just need the answer. You don't actually, just 2. You don't need to show working out because it's only 1 mark. It's that easy. And make sure the work function is positive because it's energy. Don't put that -2 in there. Question 17. Consider the following hypothetical situation. Rochelle is driving her rocket-powered vehicle along a straight test track and travels at a constant velocity between 2 timing points. The dashboard of Rochelle's vehicle shows that the time interval is this. Sandra is standing beside this track and measures the time for the rocket-powered vehicle to move between the same timing points, but records a time interval of this. So her time, basically, this one's time is more dilated. It's longer than what she measured. So calculate Rochelle's speed relative to Sandra. Give your answer as, okay, basically, we're just going to calculate velocity, the speed. Now, this is actually easy because we know this is the dilated time because, first of all, it's longer. And this is your proper time. So we can say, using the formula, dilated time is your Lorentz factor times your proper time, and we know our dilated time is 1.010, and your proper time is 1.000 times your gamma. If we find out gamma, which is basically just divided on both sides, 1.010 divided by 1, that gives me my gamma as 1.01. Now we know that, and if you don't know, we know that the basically, you know your Lorentz factor formula, you have to have it arranged. Have this formula that it's basically, this one's arranged, the rearranged formula for velocity though. It's just 1 minus 1 over Lorentz factor squared. So what we can do is, guess what? Put that c there because it's in terms of c. Just leave the c there and just basically sub that in to this formula, 1 minus 1 over. So you know how we learn our Lorentz factor is 1.01 squared. Putting that there, we should get a value of square root 1 minus 1 over 1.01 all squared. That gives me basically to how many things? So it looks like all 4 significant figures. So it'll be 0.1404 as your basically your speed. Easy, not too bad. Question 18. A hydrogen atom emits a photon of energy of 2.9 electronvolts. Calculate the wavelength of the emitted photon in nanometers. Easy. So we've got the energy of the photon and we want to calculate it. We know from the formula that oops, I'm using a highlighter here. So we know that energy is just hc over wavelength, where in this case we know that we need to rearrange it. So we want a wavelength. So wavelength over energy, if you rearrange it, so that will be what? So our h value, because we're trying to it's in electrovolts, so the energy is in electrovolts, we're going to use the Planck's constant. That's 4.1, whatever that number is again, fully forgot. I'm just going to look at my summary sheet. Where's the constant? Just want to make sure I'm double checking it. It is 4.14 times 10 to the negative 15, easy, and then times it by the speed of the light, and there it is. Doing that, so it's 4.14 times 10 to the negative 15, 3.0 times 10 to the power of 8, 2.9. Now I've got a very small number. Of course, I'm going to times it by 10 to the power of 9 to get, because you know how this is in nanometers, so you can convert it nicely. That basically gives me 428 nanometers, basically. Nice. That's a really nice question. Next question. Figure 21 shows some of the energy levels of hydrogen atoms. Draw an arrow on figure 21 that would represent the transition in part A. So yeah, you can see it's an emission. So it's an emission. So it's going down, and we're emitting 2.9 electrovolts. So what would that emit? What thing would emit that? Nothing here. It won't emit. That's 10.2. Let's see. These two would not emit 2.9. Would these two? Just let me double check that. 2.8 minus 10.2. Nope, that's 2.6. So it's close. I believe it's this one. Let's just double check this one too. So is that 13.1 minus 10.2? 2.9 was it? Yes, absolutely. So we're going for 30 point that. So there we draw an arrow, so it's emitting. So it went from n equals 5 all the way to n equals 2. That's an emission. Beautiful. Very easy. Well, Mark, a very common type of question anyway. So very easy. Question 19. Luke and Declan are investigating how the magnetic force FB on a current carrying conductor in a magnetic field B depends on the current. A diagram of the apparatus is shown in figure 22. It consists of a plastic beam to which a U-shaped current carrying loop of wire PQRS. So okay, this is the U-shaped PQRS loop. Okay, makes sense. It's attached. The plastic beam is slightly heavier at the left. So this is the plastic beam. Okay, and Dave, here it is. This is the plastic, as we can see. And it says it's slightly heavier at the left end. To balance the weight of the force, the other half, the beam is provided halfway along the, okay, so the beam is pivoted halfway along its length to balance the weight of the wire on the other half of the beam. Okay, so they put a mass here. Makes sense. A solenoid used to produce a constant uniform magnetic field B is shown. Beautiful. A solenoid with the plastic beam level, the loop PQRS, is inserted into the solenoid. A very small mass m is placed on the left-hand end of the plastic beam. The force due to gravity mg acts on its mass. Okay. A current I is then passed through the loop PQRS, creating a downwards magnetic force on the end of the loop QR. The relevant forces on the plastic beam are shown. Beautiful. So it basically so from just by looking at it, they these forces, I think they're the same. So yeah, so they're balanced basically. Okay. Alright, nothing crazy about that one. Let's look at this one. It says the current through the loop is adjusted until the beam is balanced and the downwards magnetic force FB is equal to mg. Of course, they have to be equal for it to be balanced. The current I and the magnetic force are then recorded. Luca and Declan repeat the experiments with different masses. Complete the following table below by providing one variable from the investigation for each classification. Okay, what is the independent variable? Remember, the independent variable is the variable that you manipulate or change. In this case, it is absolutely the math because can you see here? Where is it? Can you see how they're saying Luca and Declan repeat the experiment with different masses? They're playing around with the masses, or that's what they're affecting. So we can say masses. Next one is the dependent variable, which is the variable that is you're measuring. Now, they're actually measuring two things. The current, they said, look, current and magnetic force are then recorded. So we can say kind of, you just have to write one, but yep, so current is something. You can put current or the FB, which is your magnetic force. And the control variable is the variable that is constant throughout the experiment. Now, they did say, luckily, that the magnetic field is constant and uniform. So, oopsie, constant and uniform. So we can just say magnetic field. In that case. Beautiful. Can you explain, so it says explain why the effect on the magnetic field on the two sides of the U-shaped loop, PQ and RS, which is that. PQ is that part, and RS is this part here. All right, makes sense. So these two parts, that one and that one, these two sides, yeah, has not been considered in the experiment. Wait, so explain why the effect of the magnetic field on the two sides of the U-shaped loop, PQ and RS, have not been considered. That makes sense. Well, first of all, they're only playing around with QR because why? Well, if you draw a field line, if the solenoid current passes through it, it will create a magnetic field that will look like this. I'm making it up, but this is how suggest that this is the north pole of it. So it'll look like this. Where this is, look, it's coming out and it's coming back here. Okay. Now, the most important thing is I've just drawn an example, but imagine, okay, the field lines are going to go passing like this. You see that? The fields are going to be passing like this. You see that? Now, what's important is I'm just going to draw these two, for example. But can you see how the field lines are actually parallel to those lengths over here, the P, Q, and RS. And of course, what happens if they are parallel? Then the force is zero. The magnetic force is zero. Remember, they have to be perpendicular. Yeah, both the magnetic field and the side have to be perpendicular for a force to be produced. Remember, by your right hand slap rule. In this case, can you see how they are parallel? This magnetic force that will be produced from the solenoid is parallel to the both sides, hence it's negligible. That's why. Whereas in this case, why is this important? The QR, because can you see how it's perpendicular? And that is why we only focus on that. That's actually very nice. That question is actually not too bad. So let's write. Okay, so something simple like say the magnetic field is parallel to both sides. Hence the magnetic force on each side is 0 newtons. Beautiful. Next question. It is important that the beam is pivoted at its center. Explain why this is necessary. So look, you can see this here is pivoted into the center. Why is it? Now, of course, the most important thing is, like, if one is not, if one's larger than the other, it basically rotates, doesn't it? So I think what they kind of want you to do is explain it by using torque. Is that what they're doing? And it would make sense. For example, we know like torque is force times your R, where R is basically this. So if this is the lever, so okay, what it is this is the arm. So let me draw it red. So this is the arm here. This is the arm. So this is your radius. And this is the force, which is your F, yeah? And so so imagine that you calculate the torque and you get a torque of this, yeah? Now, because both are actually, you remember mg and these two forces are the same. And of course, they have to be equidistant because these two R's have to be the same, yeah? Can you see how these both are? Yeah, have to be the same. And because mg, which is this force, is also the same, wouldn't this also torque be the same? These two torques have to be basically cancelling each other out. Like a no net torque, basically, in another case. They have to cancel each other out. And so they can be balanced because if one is larger than the other, then there's going to be a rotation. Remember what the point of torque is? For rotation to occur, yeah? Does that make sense? So I think that's what they're kind of asking us. So in this case, the way you would explain it is that these two lever arms have to be the same because these two forces are the same, hence the torques will be the same. Does that make sense? By using torque here? I think that's how I would explain it. I don't know what... I think that's the only thing that would come to my mind because, yeah, I would approach it like that. So let's write something. So we can say... it's important that the beams pivot at the center. We can say pivoting at the center makes the lever arm equal. Arms actually equal. Therefore, when the beam is balanced, equal torques, I'll write the formula, I would say, so torque is force times R, acts on both sides, resulting in no net torque, and no rotation, That's why you have to make sure it's at the center. Alright, that sounds okay. I hope that's correct. D, each time Luca and Declan change the mass, they adjust the current to rebalance the beam. So they repeat the measurements for each mass 5 times and calculate the average. State the importance of taking repeated measure. Very, very easy if you're doing chemistry or anything. We repeat, it's only 1 mark. So we repeat measurements to what? To reduce random error. That's the point. It's to reduce random error. So just write, reduce, what happened there? Just say, reduce random error. That's all you have to write. Reduce random error. That is the point of repeating an experiment error. Because it's 1 mark, I think you just need to write that actually. And I think that's it. The results Luke and Declan obtained are shown. Okay, we got the magnetic force and the average current. The uncertainty measurement of the current is plus or minus 0.2 amps. The uncertainty in the measurement of force is negligible. On figure 24, plot a graph of the data in table 1 with current on the vertical axis and magnetic force FB on the horizontal axis. So they've already done that for us. You must include uncertainty bars and a trend line. You may assume that the trend line passes through the origin. Okay, so it must pass through the origin. Let's do that. So how do we make these? Okay, how do we... So the magnetic force are going like 0, 120, 240, 360. How many are there? So I would say each of these little squares, I'll say for the magnetic force will be like 20. We'll go by 20s. Like this is 20, like 20, 40, 60, 80, 100. So we'll go basically like that. So hopefully it fits all of them. 100, 200, 300, 400, 500, 600, 700. Does that fit all of them? Yep. And the other one, the average current, it's going by 1, 2, 3, 4, around that. So we can say like this is 1, 2, 3, 4, 5, and it should fit all of them, where each is like 0.2. It goes by 0.2, which is good because that's also our uncertainty by 0.2 amps. Let's put them now. Let's graph them. So the first one is 0, 0, so it starts at 0, 0. So I'm just gonna put a red dot here. 0, 0. Next one is 121. So 120, which is here. So if I draw a line, this is where the 120 is, and 1 is here. So I'm gonna sketch that, rub that out. So that's that point. 240. Where's 240? 240. So it's right over here. 240 what? 242. Which is over here. Get that one out. The next one is 360. 246. So here. Okay, and what is the... So it was it 360? Yeah, 363. Done. Then 600, which is over here. And the value is 4.6. So 4246 is right over here. Done. So let's draw those uncertainty bars. Now it's by 0.2 amps, which is basically 1 square down, 1 square up, and it looks like that. Beautiful. So what I'm going to do is, because they're all identical, I'm just going to take that and just duplicate it. Make sure that they are the same. There it is. Done. So we've done the uncertainty bars, and we have to draw a line of best fit, and trinity line. So I'm going to draw this line. It has to pass from 0, and it goes like this. Now that's to pass through everything. So I would say this is where it passes quite through everything, like, because this is a problem. This one right over here is trying to fit it, like would say around here, would fit perfectly. So look, it hits it right at the end there, but also it hits this one, so it's fitting everything. And I think that's the best line of fit. Is that it? You must include... Wait, let's read it. You must include uncertainty bars. We've done that. With a trend line, we've done that. You must assume that the trend line passes through the origin. Yep. And that looks beautiful. And that's it. That should be good. Next question. Using your graph in figure 24, calculate the gradient of the trend line. Show you're working out. Very easy. So we just need to pick 2 points and calculate the gradient of those 2 points. So 2 nice points. Like I can see this point is crossing nicely, so I'm just going to take that point. So which is right over here and right over here. So that was 1 point. Another one that crosses nicely is this one over here. There and there. Now we just need to actually calculate them. So m, which means gradient, is equal to what? Okay, so let's calculate that. So this one here is 2.4, so it'll be 4.4. This one here is 1.4, because like 2.4. Yep. This one here is 246, so this will be 560, and this point here would be 180, because 2468. Yep. So we got everything now. So it'll be 4. So it'll be the y value, so 4.4 minus 1.4 all over 560 minus 180. And don't forget, times it by 10 to the negative 6. That's where the silly mistakes can happen. All right, see what that will equal to. It's the gradient. 4.4 minus 1.4, 560, 180 times 10 to the power of -6. That gives me around, rounding it up, 7,900. Beautiful. Oopsie. Let me draw it in a nice yellow. Like that. So that should be our gradient for that one. Hope it's correct. Next question. Luca measures the length of the wire to be 2 centimeters. Use this length and the value of the gradient to estimate the strength of the magnetic field. Okay, very common question. 3 marks. Love it. So we know for a fact that we're going to have to use this formula. FB, so force equals N, like basically N, L, I, B. Okay. Now, because it's just one wire, so we don't, N is 1, so that's good. Now, what we need to kind of work, okay. Our gradient, yeah, which measures the Y divided by, you know, your current, which is I, over the magnetic force, so I over B. What our basic gradient gives us, you know our M value here, which is our gradient, it gives us I over B, F, which is the force, yeah? So remember, it's always Y, which is the Y-axis, which is in this case current, over the force. Just double checking. Yep. Okay. So what we need to do is we need to rearrange this over here to make I over F. Now, the way that I'll do that is do it like this. So I'm going to divide both sides by I over B. So I can get rid of these. Done. So what am I doing? Sorry. I'm going to... What am I doing? Okay. Let's think. Let's take a time. So actually, what I'm going to do is I'm going to divide both sides by LB. L and B, so LB on this side and LB on this side, okay? Because that will cancel out this and that. Beautiful. So we're left with current as that. So the current, yep. And then what I'm going to do is I'm going to multiply both sides by 1 over F. And the same with this, 1 over F. Why? So we can actually cancel this F out. And so, and then multiply these two, we get basically, let me kind of work this out. Okay, so current over F, which is current over F, is equal to 1 over LB. So the length B, beautiful. Well, you remember this is your gradient. This is equal to your gradient. Done. So what we can do is we can, because our goal is to find the magnetic field, so we can actually rearrange this to fit our thing. So if I multiply both sides by B, these B's cancel out. And so you're left out with like that. So it'll be MB, and then I'll multiply both sides by 1 over M. That gives me, basically, these cancel out, and hence B would be equal to 1 over, oh my god, so 1 over M over L. That is our formula, basically. That is the jackpot. We've hit the jackpot. This is what we want, this formula. So we want to calculate the magnetic field. It's done. We've got the formula. Let's do it. So that means it's 1 over the gradient. M is the gradient, which we found out was 7,900 from the last question. And the length of QR, which is 2.0 times 10 to the -2. Remember, make sure it's in meters. That gives me what? 1 over 7,900, 2.0 times 10 to the -2. That gives me basically, it's a very small value. So to 2 significant figures, we'd say 6.3. 6.3 times 10 to the power of 1, 2, 3. -3, yep. So 1, 2, 3. Beautiful. That looks not too bad. So it's not too bad. Very common type of question dealing with the gradients and stuff. Next question state, what would happen to the magnetic force if the wire QR was shorter than the length? Easy. So what is this supposed to be the last question? I hope I'm doing it right. So, you know, by using this formula, FB equals N L current times B. Of course, if you decrease the length, which is QR, you'll decrease the force. Isn't that correct? Isn't that quite easy? Yeah. So, yeah, I don't know. Is that what would happen to the magnetic force if the QR was shorter than length? Yeah. I'm just wondering, like, is there anything out? Like, am I supposed to, like, say something? Like, am I supposed to? Because the question is quite bland. It's just, so I'll say from this, decreasing L, I'm really tired, by the way, would decrease the magnetic force. Done. Alright, so yep, from this, decreasing L would decrease the magnetic force. Now, I'm still unsure. Like, state what would happen to the magnetic force FB if QO was shorter than length. Yeah, like, isn't this just obvious? Like, do the formula, or is there something like we have to deal with? I don't know, but do we have to deal with something like complicated if it's a lot? I'm not too sure, but I think it's this simple. I'm hoping it's this simple. I'm not surprised if this. I'm hoping it's correct when the examiner's report come out, but I'm hoping that's correct from what I think, because I'm already drained from this exam. It was not a bad exam. I liked it, but this last question maybe is it too simple? I would say I'm not too sure. I hope it's the easy. Like, I hope it's like it's supposed to be easy, and so it's just this answer. But yeah, thank you guys for watching. Please make sure to like and subscribe for more future videos like this. I hope you guys enjoyed this video, and yeah, please take care of yourselves. Bye bye.